Hi everyone, welcome to the Department of Physics seminar. We have with us today our own student, who used to be a student at least a few years ago, Haider Khan. After completing his undergrad from LUMS, he went on to do on to he went on a grand tour of Europe funded by the Erasmus program, and is currently doing a PhD at the Center for Theoretical Physics in Warsaw, Poland. We welcome you to our seminar series, Heather, and we hope you'll keep coming back to your alma mater with more and more interesting talks. Please go ahead.
Yeah, thank you so much, Dr. Rizwan, for the kind introduction. Once again, I'm Haider Khan, currently a first-year PhD student working in gravitational lensing of gravitational waves at the Center for Theoretical Physics in Poland. I was a graduate of LUMS with a degree in physics in 2022 before starting my master's in astrophysics and space science. It was at the University of Bremen in Germany where I completed my master's with my master's thesis titled "Lensing Shadow and Photon Rings in a Black Hole Magnetized Black Hole Spacetime" under the supervision of Dr. Volker Perlet. And we recently got to publish a paper in Physical Review D, and it will be the results of this paper that I will be sharing with you today. So if you are not well aware of what these terms really mean, so don't get intimidated, because I will be explaining each one of them individually as we go on through this presentation. I would presume that the audience mostly for this presentation includes undergraduate students. So I will try to go into the very basics of what are some of the terms that I'm discussing. But still, if you have some idea of having taken a course on general relativity, it might be very useful for this presentation. Okay, so let's get started. So first of all, as for the abstract, a quick look, I will be talking about gravitational lensing, in particular shadow and photon rings in the Ernst spacetime. I'll let you know what this means. I'll be sharing some analytical results about the horizontal and vertical angular component of the shadow, and finally we'll find a way to characterize the relative separation between individual photon rings. Okay. So, and very naively, let's get started with what gravitational lensing really is. So, gravitational lensing basically is the deviation of electromagnetic or gravitational waves, or simply light, when it passes through some sort of the gravitational field of a massive object. So, this figure that sorry, can you guess? Yeah, okay, never mind. So this figure really illustrates the idea of gravitational lensing pretty well. Let's assume that you have a light source somewhere on the left side of your screen. It is producing these electromagnetic waves in all sorts of directions. And then there is a massive object that disrupts the space-time around it. So from general theory of relativity, we know that space-time is, in a way, it's affected by the gravitational field of massive objects. And when light or electromagnetic or gravitational waves passes through this gravitational field, it deviates from its original trajectory. And here you have a focus of these electromagnetic waves. And if you put put an observer over here, and they try to trace back the light-like Jurassic that they have received, without the knowledge of the gravitational lens present here, they might trace the apparent position of these light rays to be very different from where they are originating from. And it is to the gravitational lensing that the deviation of these waves is happening. So this is the very naive definition of what gravitational lensing really is. So gravitational lensing proved to be one of the first experimental tests of general relativity. The theory came out in 1915, and it was in 1919 when Sir Arthur Eddington performed this experiment during a solar eclipse. And stars who may have otherwise been behind the sun were still visible from Earth because of the sun's gravitational field serving as a gravitational lens and deviating the light, and that was received on Earth. And through this deviation, you could essentially test whether the relativity was right about gravitational lensing or not. And after this, sorry, can you mute yourself? Yeah. Okay, and after this first experiment of gravitational lensing, we have had a major advance in the theory, and now multiple astronomical and astrophysical tests have been conducted since. Okay, so these are some of the important terms that I would like you to know before we go on with our presentation. So light like geodesics just simply corresponds to the path that light takes. It could be photons, it could be gravitons. Similarly, time like geodesics is the path that freely falling massive objects follow. By massive objects, I don't necessarily mean huge objects, but any object that has a non-zero mass and is free falling goes through a path that we call the time-length geodesics. Shadow of a black hole is the dark silhouette of the black hole that we essentially cannot see. And the other terms I will explain as we go on. Okay, so when I say that I'll be talking about gravitational lensing in a magnetized black hole spacetime, what does the magnetized black hole spacetime really mean? In physics terms, we call it the Ernst spacetime, which is also known as the Schwarzschild-Melvin spacetime. And it describes a Schwarzschild type black hole that is non-rotating, uncharged, spherically symmetric, and it is present in an external magnetic field universe that is homogeneous and uniform everywhere. So before we look at the definition of the space-time, let's have a look at what the space-time really looks like. So imagine a Schwarzschild type black hole that is spherically symmetric, and it looks something like this. And then you put this black hole into an external magnetic field. So the magnetic lines of force in this case are along the z-axis of the space-time. So this is what the Ernst spacetime essentially looks like. If you look at the definition of the metric over here, the metric looks remarkably similar to what you have already known as for the Schwarzschild spacetime. In fact, except for the lambda factor, the rest of the metric terms are exactly the same as the Schwarzschild-Melvin spacetime, the Schwarzschild spacetime. However, it is the lambda factor that makes a remarkable difference in this case, and the lambda is where you introduce the magnetic field strength through this term over here, which is P. So if we talk about some of the limiting cases of the Ernst spacetime, we find out that if you take away the magnetic field, or if P is equal to 0, the spacetime itself reduces to the Schwarzschild black hole solution, which once again describes it's a vacuum solution of the Einstein field equations, describes a spherically symmetric, uncharged, non-rotating black hole. And in a similar manner, if you take away the black hole itself, or you put mass equal to 0, you reduce yourself to a Bonner-Melvin magnetic universe, which once again just describes this universe with magnetic lines of force that are homogeneous along, let's say, the z-axis in this coordinate system. And this is something that you should really expect as well, right? So if you take away the magnetic field, you're just left with a black hole. If you take away the black hole, you're just left with a magnetic field. And this is what these are two limiting cases of the Ernst spacetime. Okay, so let's now discuss some of the properties of the Ernst spacetime. So I would like you to go back to your classical mechanics course. You remember that if you have a Lagrangian that is independent of the time coordinate, as a result, the energy of the geodesics E is conserved. The spacetime in this case is also independent of time coordinates, so it's said to be static. And energy E of the geodesics just stays the same. So energy E is a constant. Similarly, the spacetime is also independent of the phi coordinate. And as a result, the spacetime is said to be axisymmetric, and the Z component of the angular momentum L is also conserved. The spacetime has a remarkable difference from the Schwarzschild spacetime in the sense that it is not asymptotically flat. That means that if you take R approaching infinity, the spacetime does not reduce to the Minkowski spacetime, but rather it reduces to the Melvin-Bonner magnetic universe, something that we have talked about already. And finally, despite the presence of an external magnetic field, the event horizon of the black hole still stays at R equals 2m, much similar to what you have for the Schwarzschild spacetime. Okay, and one more important property of the spacetime is that the spacetime is chaotic. By what is chaotic, you may ask. Spacetime is said to be chaotic if the geodesic equations are not completely integrable. Go back to the Schwarzschild spacetime. When you try to solve the geodesic equations, you have the same number of constants of motion as the number of equations or the number of variables that you want to solve for. If you go back to the curved spacetime, which describes another black hole solution that is also rotating, you have 4 constants of motion and you have 4 variables to solve for, and you can solve for it completely analytically. But when you come to the Ernst spacetime, you find out that you only have 3 constants of motion and 4 variables to solve for. The 3 constants being the energy E, the Lagrange, the angular momentum component ZL, and finally the Lagrangian itself. However, you have 4 variables to solve for, and as a result, because of the system being incomplete, you cannot solve the geodesic equations completely analytically. However, and in this case, we call the spacetime to be chaotic. However, there are still certain results that we can extract from this spacetime by restricting ourselves to certain planes and making sure that in those cases you have enough constants of motion. And these are the results that I will be sharing with you over the course of this presentation. Okay, so first of all, let's talk about circular light-like geodesics. So what are circular light-like geodesics? These just correspond to the radial values at which light can go in a circle around the black hole. So let's draw a comparison, first of all, with the Schwarzschild spacetime, something you might be familiar with. So in this coordinate picture, the Schwarzschild spacetime has a singularity at r equals 0, and then there is an event horizon at r equals 2m. And then outside of 2m, there is another special radius that we call the photon sphere at r equals 3m. And photon sphere corresponds to the radius value at which you can make a whole sphere on which light-like geodesics move in a circle. So wherever you are on the surface of the sphere, there are an infinite number of light-like geodesics that would be moving in a circle. This is the theoretical radius value at which you could say that if you could stand at this value, theoretically, you would be able to see the back of your own head because light is moving in a circle. So for the Schwarzschild black hole, you have this sort of a behavior at r equals 3m, and there's only one radial value at which light can go in a circle. The remarkable difference that you have for the Ernst spacetime is that, first of all, you don't have a sphere of this sort, but rather you have to stay restricted to the equatorial plane. And secondly, in the equatorial plane, you have not 1, but 2 of these radial values at which light can go in a circle. And these are the radial values that we identify as R1 for the outer radius and R2 for the inner radial value. They are the solutions to this cubic equation, and they exist when the magnetic field strength is smaller than a critical value, which is identified over here. So when the magnetic field exceeds this critical value, the solutions merge, so they don't exist anymore. So for the rest of this presentation, we will be talking about magnetic field that is smaller than this critical value. Okay, so moving on, where do these circular light-like geodesics come from? So they are solution to basically this effective potential. Like if you try to get the critical points of this effective potential, the circular light-like geodesics correspond to those critical points. So let's just look at the very beginning of this GIF. This GIF is showing you the behavior of this potential when the magnetic field increases. But when magnetic field is 0, that corresponds to, as I told you, the Schwarzschild spacetime. And in the Schwarzschild spacetime, we are aware that there is only one such critical value that corresponds to the maximum over here at r equals 3m. That is something I just told you is called the photon sphere, and it's unstable because this is a global maximum. This is because as the potential increases, the value becomes smaller and smaller, and it eventually dies off at r equals infinity. However, as we turn on the magnetic field and we make a transition from the Schwarzschild spacetime into the Ernst spacetime, we find out that this potential does not die off at infinity, but rather it blows up. So at r equals infinity or asymptotically, this potential also goes to infinity. And that is the reason you don't have just one critical point, but rather 2 of them. Let me show you those here. So if you just look at these 2 curves, you see that there is a local maximum over here, somewhere close to r is equal to 3m, as in the Schwarzschild case. But then you also have a local minimum that corresponds to the other circular light-like geodesics. So these are the 2 critical points that correspond to the 2 radial values at which circular light-like geodesics can exist. R2 is the smaller radius, and it corresponds to a maximum and is hence unstable. R1 corresponds to the bigger radial value, which is a local minimum, and it is stable. And yeah, so these are the circular light-like geodesics that exist in the equatorial plane of the space-time. As soon as the magnetic field strength hits the critical value, you see that both the critical points merge into a saddle point, and as soon as the magnetic field goes above the critical value corresponding to these two curves, the critical points disappear, and you don't have any stable or unstable circular light-like geodesics anymore. Okay, so now that we know about circular light-like geodesics in the Ernst spacetime, let's talk about circular time-like geodesics. And before we talk about these in the Ernst spacetime, I would like to bring your attention once again to the Schwarzschild spacetime. So as I told you, in the Schwarzschild spacetime, singularity exists at r equals 0, the horizon at r equals 2m, and the photon sphere at r equals 3m. And then as you go beyond r equals 3m, in the Ernst, in a Schwarzschild spacetime, you can have circular orbits for any radial value. So this means that r is equal to 3m is the lower boundary that exists for circular time-like geodesics. And as you go beyond this boundary, you can have a massive object that can orbit the Schwarzschild black hole for any radial value that may exist. And this radial value can be extended all the way up till infinity. However, we still try to make a distinction between stable and unstable orbits. And this is where another radial value comes in, which is defined as at r equals 6m. This is what we call the innermost stable circular orbit, and short for ISCO. And this is the value beyond which, outside of which, you have stable circular time-like geodesics, and between r is equal to 3m, the photon sphere, and this value, you have unstable circular time-like orbits. So the major property over here that I would like to emphasize on is that in the Schwarzschild space-time, the stable circular the time-like geodesics can be extended all the way up till infinity. You can think of any radial value, and you can essentially have a circular time-like orbit at this radial value in the Schwarzschild space-time. The remarkable difference that we have from in the Ernst space-time is that these circular time-like geodesics cannot be extended all the way up till infinity, but rather exist between the two circular light-like orbits. So go back to this image, and you see that R1 and R2 correspond to circular light-like orbits, and the circular time-like orbits only exist between these two. So that's a remarkable difference, that you not only have an inner boundary, but rather an outer boundary as well, beyond which the circular time-like geodesics cannot exist. And this will have very important implications when we later talk about photon rings. Okay, this is a very nice animation that shows you the behavior of these geodesics. So the vertical dashed line in this case correspond to R2 and R1, which once again are the circular light-like geodesics. And you see that the time-like geodesics, which are circular, can only exist between these two values. So the plot over here is not of the potential, but rather the second derivative of the potential. And if there is something that we know of from our calculus classes, is that the second derivative is used as a test to see whether the critical points are stable or not. And you see where the second derivative is positive, it corresponds to the stable geodesics, and where it is negative, it corresponds to the unstable geodesics. So beyond the point where it intersects the x-axis, something that we will also be calling ISCO, or the innermost stable circular orbit, the time-like orbits are stable in this region. And you see that it is rather bounded on the outside. So this boundary is something that we can also call the outermost stable circular orbit, or OSCO for short, something that is non-existent in the Schwarzschild spacetime. Okay, so now let's move on to a conformal relationship. What does that mean, you may ask? So first of all, from general relativity, we know that if two spacetimes are conformal to each other, the behavior of light-like geodesics is the same in both of them. Now, conformal relationship really means that the two spacetimes can be written in this form, that if you multiply all the terms of one spacetime with a single factor, or known as the conformal factor, you recover the other spacetime. So this is basically the conformal relationship, and we were very lucky with this relationship that we found out. Don't get intimidated by the math that we have here, that in the Ernst spacetime, if you reduce the spacetime to a meridional plane, the spacetime becomes conformal to the Schwarzschild spacetime. What does a meridional plane mean? You remember that azimuthal coordinate goes from 0 to 2 pi in the equatorial plane. And if you fix the value of the azimuthal coordinate, you are said to be restricted to a meridional plane. So you can fix the value to 0 pi, you could fix the value to, I don't know, pi half or whatever you like. And if you are in this plane, the space-time is conformally equivalent with the Schwarzschild space-time. So let's look at the first term over here, which is just the Lagrangian of the Ernst space-time. And since phi is a constant, that would mean that phi dot in this case is 0, and you're left with this. And now you see that the lambda squared factor is common in all of these terms. So you just take the lambda squared factor out, and as a result, what you are left with is the Schwarzschild space-time in the meridional plane. And since we know that if two spacetimes are conformal to each other, the behavior of light-like geodesics is the same. Therefore, all the results that we were aware of for the Schwarzschild spacetime are also valid in the Ernst spacetime for light-like geodesics in a meridional plane. And one of the results that I've already discussed with you is the behavior of a photon orbit. So in the Schwarzschild spacetime, you have a photon sphere at r equal 3m, where light goes in a circle. And if you intersect that with a meridional plane, you are left with a photon orbit. And the photon orbit is something that will now exist in the Ernst spacetime as well. So this was a remarkable result that will have great consequences for the calculation of the black hole shadow and photon rings later on in this presentation. Okay, so what is the black hole shadow? So if you look at this image, this was one of the first images of a black hole ever captured. This was a supermassive black hole at the center of the M87 galaxy. I think this was a second image after they performed some corrections for the polarization of light, but we're not concerned with that. If you look at the very middle or the very center of this image, you see a dark shade that corresponds to the black hole shadow. It's the part of the black hole that we cannot see. So how do you calculate the boundary of this black hole shadow? Let me share that with you first of all. So let's assume, first of all, that we are in the Schwarzschild spacetime, once again, spherically symmetric, non-rotating, and uncharged. And you fix an observer at a radial value r0 somewhere outside of the horizon of the black hole. Now, from the observer, you trace the time backwards into the past. So you say that you reverse the time, and now you divide the light-like geodesics that are coming out of this observer into two categories. There is one category of light-like geodesics that can go all the way back to some sort of a light source that is present over here. And if you consider these light-like geodesics, then since they are being traced back to light sources, they will produce bright images in the observer sky. And you can see these images for the observer. And then there's the other category of light-like geodesics. These are the ones that can be traced back all the way to the black hole horizon. And since they're not coming from a light source, as a result, they will produce dark images in the observer sky, or basically you can associate that with the darkness in the observer sky. And this is something we call the black hole shadow, because there's nothing coming out of the black hole, so it's just dark. And then you can make a borderline case between these two categories. And this borderline case corresponds to the light-like geodesics that don't go to the light sources, that don't go to the black hole horizon, but rather trapped around the black hole because of the light capturing regions. In the case of the Schwarzschild spacetime, I told you that you have a photon sphere at r equals 3m. And it's unstable and it acts as the light capturing region. So in the case of the Schwarzschild black hole, the photon sphere serves as the boundary of the black hole shadow. So this is how you calculate the black hole shadow in the Schwarzschild spacetime. And in the Ernst spacetime, something similar happens. However, I would like to take you back to the slide that the Ernst spacetime is chaotic, which means that we cannot solve the geodesic equations completely analytically. This means that the complete boundary of the Ernst space-time black hole shadow cannot really be obtained because you don't have the analytical expressions for it. However, if we restrict ourselves to certain planes, we can extract some properties of this black hole shadow. And this is what we will do. We will restrict, first of all, ourselves to a meridional plane. And that will help us obtain the vertical component of the vertical angular component of the shadow, and then we'll restrict ourselves to the equatorial plane to get the horizontal angular component. And since I shared with you that in the meridional plane, the black hole is conformal to the Schwarzschild spacetime, therefore the expression for the vertical angular component of the shadow is the same as what you get for the Schwarzschild And yeah, so if you calculate the angle for the Schwarzschild black hole, this is the angle that comes out, and this is the same angle that we get for the Ernst space-time vertical angular radius as well. The horizontal angular radius is somewhat complicated to obtain, and I will not go through the complete calculations over here. But in the case of the horizontal angular radius, you just use the light-like geodesics that exist in the equatorial plane, and the inner light-like geodesic that I showed you is unstable. That corresponds to this critical point over here is what contributes to the inner horizontal angular radius of the shadow, and this is the expression that you get. Okay, there's more subtleties around it depending on the light sources where they are. I will not talk in much detail about that, but the important result that you should know is that we found out analytically that the shadow of the black hole is oblate, which means that the horizontal component is always bigger than the vertical component of the angular of the shadow. And this is what this is a nice animation that shows you these results as you start increasing the magnetic field. So at the very beginning, the shadow seems circular. That is the case for the Schwarzschild spacetime because B is equal to 0. But as soon as you start increasing the magnetic field, the shadow becomes more and more oblate. This result may be a little counterintuitive. At least it was counterintuitive for me because I told you that the magnetic field is along the z-axis and the black hole oblateness occurs in the other direction. But that's just how it is, and the black hole becomes oblate. That means the horizontal component is bigger than the vertical component. This image is rather exaggerated as well. The oblateness might not be this huge, but it's just for the sake of visualization. Okay, let's move on to the last topic of the presentation, something I think that is the most exciting for me. It's about the photon rings. So photon rings correspond to light-like geodesics looping around the black hole multiple times before reaching the observer. What does all of that mean? Let me show you with this slide over here. So let's imagine that you have a black hole, and around the black hole, you have these light sources in the equatorial plane that are moving in a circle. So they are essentially the time-like circular orbits in the equatorial plane, as we have already discussed. Now, there are various ways of light from these sources to reach the observer, which in this case we'll assume to be at one of the poles of the black hole. So there is one case where the light sources light rays just directly reach the observer. And since these light sources are in a circular orbit, they will produce a ring of images in the observer sky, something that we call the primary ring or ordered zero image. Now, there is also a possibility that the light rays go around a half loop black hole and then reach the observer. And since once again they're in a circular orbit, so they produce another ring of images. This is something that we call the secondary image, secondary ring, or order and n is equal to 1 image, and it corresponds to 1/2 loop that the light rays make around the black hole. Then there's also a possibility of light making a full loop around the black hole, contributing to the tertiary image or the first higher order ring. And this is what we call the n is equal to 2 order image. And you would see that as you make more and more loops around the black hole before reaching the observer, the ring becomes dimmer and dimmer, and it becomes closer and closer to the black hole shadow. Essentially, you can make an infinite number of loops around the black hole, so you can have infinite order images, but it's usually the first couple of order of rings that we concern ourselves with. Okay, so you can quantify the radius of these individual rings through a factor over here. You don't need to, there's no need to understand what all of these individual terms mean, but this is just the expression that quantifies the radius of an individual photon ring of order n, let's say. So if you just put n is equal to 2, this will just give you the radius of this ring, and 1 will give you the radius of this ring, and so on. And the most important factor that we need to consider in this case is the relative separation between these two individual photon rings, something that we call the gap parameter, which is given by this delta factor over here. So this just quantifies the relative separation. Let's say if you have the gap parameter of order 2, it would essentially mean you take the radius of order 2 image and subtract the radius of order 3 image from it, and then just normalize it by the radius of order 2 image. So this is what we call the gap parameter. Now, from the literature, it was found out that the gap parameters for different spacetime of a particular order is characteristic of that spacetime if you consider its ranges. What does all of that mean? If you let's restrict ourselves to the Schwarzschild spacetime, and I told you that in the Schwarzschild spacetime you could have time-like circular orbits from an ISCO all the way up till infinity. So ISCO corresponds to the innermost stable circular orbit, and then you can keep on increasing the radius of these circular orbits, and you can extend them for as long as you want. Now, if you determine the value of gap parameter for, let's say, order 2 at ISCO, then you get 1 point of the gap parameter value, and then if you determine the value all the way up to infinity, you get another point, and this brings you this gets you with a range of these values. So something that you have over here. So let's unpack this plot very easily. So you have the magnetic field strength on the y-axis. B is equal to 0 corresponds to the Schwarzschild case, that is when there is no magnetic field outside. And if you assume that your light sources are present at ISCO and you obtain the value of the gap parameter of order 2, this is the point that you will get for the value of the gap parameter. And then you extend the light sources all the way up till infinity, and you find out what the value of the gap parameter is. It comes out somewhere over here. And this range is the range of the gap parameters of order 2 that you can get for the Schwarzschild case. And this range is said to be characteristic of the Schwarzschild case. And then you go on to a different spacetime. For example, you consider a Kerr black hole, you consider the light sources at ISCO all the way up till infinity, and you see what the range comes out to be. And the range will be different for the Kerr black hole than the Schwarzschild black hole. You could consider a wormhole, you could consider some other spacetimes, and you would see that all of these ranges differ. And in essentially, these ranges will help us distinguish between individual spacetimes. And this is something that we did for the Ernst spacetime as well, that we started increasing the magnetic field strength, and we saw how the gap parameter values or ranges really change. Remember that in the Ernst spacetime, you cannot have the time-like geodesics extended all the way till infinity. So these ranges correspond to the ISCO for a given magnetic field value all the way up till OSCO. And then you start increasing the magnetic field and you get all of these different ranges. And these ranges can help you distinguish between the Ernst spacetime of different magnetic fields and also the Schwarzschild spacetime as well. So I would like to end on this comment that if one day we are hopeful to build a telescope that is strong enough that it can resolve individual photon rings around a black hole, then we could use these results to ascertain whether the black hole has some sort of a magnetic field around it or not, and what the value of that magnetic field really is. Okay. In summary, we talked about circular light-like and time-like geodesics in the equatorial plane about the z-axis. The results of spherical geodesics I did not share with you, and neither did I share the angular deflection expressions with you. But then we talked about the shadow angular diameter expressions for the Ernst spacetime, and finally we discussed the photon rings and the gap parameter. This is the paper that we recently got to publish in Physical Review D, so you are welcome to check it out. I can have a longer discussion with you about the results that I did not share. And yeah, these are some of the resources that we used. And yeah, I think now I'm ready to take any questions.
All right, thank you, Haider. So are there questions?
Yeah, we have Sarim.
Assalamualaikum. Yes, I just had two questions. One's a minor question. You talked about how the Ernst spacetime and Schwarz spacetime have a conformal relationship. So you talked about how
Yes.
the photon ring is at r is equal to 3m, if I'm not mistaken. So is that also true for the event horizon?
Yeah. So the event horizon, as I discussed in the very beginning of this talk, the event horizon stays the same at r equals 2m. So the event horizon does not stay there because of the conformal relationship. Because remember, for the conformal relationship, we have to restrict ourselves to the meridional plane, but the event horizon just exists for all the planes. So it's not because of the conformal relationship, but it's rather just because of the geometry of the space-time that r equals 2m is the is the radial value at which this term blows up. So that's the reason the event horizon is at r equals 2m. So the same as Schwarzschild.
Okay, and the second question was regarding, I think it's one of your slides. You talked about R1 and R2. I'm not sure which slide that is.
Yes, this one, hopefully.
The one probably after.
Maybe this one.
It was about the comparison of ice core. Yeah, it was there. Yeah, the slide before.
Okay. Yeah. Oh, the slide before. Yes, this one.
Sorry, I think it might be ahead. It's
No,
where
but go
you
on.
compare within
Explain
an
and I
inequality.
can.
Yeah. So you defined R1 as ice core here, yes. So what is R2 exactly then?
No, so R1 is not ISCO.
Sorry, it's Osco, yes, with the O. So what's
Yeah,
R2
ARCO is
then?
OSCO. Yeah. R2 in this case, I mean, it's not exactly related to ISCO or OSCO. R2 is just the radial value at which the inner circular light-like Jurassics exist. So let's go back to this plot. This will be more helpful. So I told you that there are two radial values at which you have circular light-like Jurassics in the equatorial plane. R1 is the value which is the larger one, and R2 is a smaller radial value. And R2 is something that is closer to the photon sphere as if you consider the case of the Schwarzschild black hole. So R2 is the inner one, and R1 is the outer one. R2 is unstable, while R1 is stable. So yeah, that's it.
Okay, thank you.
Of course.
Right. So, do we have any more questions?
I have maybe a very quick question. So the gap parameter that you potentially could be used to determine the kind of structure of your black hole or whatever, if you have a precise enough telescope, right?
Yeah.
I'm not very familiar with this stuff at all, so maybe this is a redundant question, but do you expect large enough differences between, say, so this is obviously measurably different from the Ernst spacetime to a Schwarzschild, but say a Kerr or Kerr-Newman or a million other different black hole types will have their own gap parameters that surely fall within similar ranges.
Yeah.
So do you think it is a feasible method to check, or is it just another one along a list of other checks to include, if you know what I mean?
Yeah, I get that. I wish I had the plots from the original paper that I was following. I think the paper was Ratore, Tsukko, and Perlich, where they gave these ranges. I think in the ranges are quite different for these different space times. In our case, yeah, you do have some overlap, of course. So maybe if you find a gap parameter value somewhere over here, you cannot essentially say whether it's a Schwarzschild black hole or an Ernst space-time with some different magnetic field strengths. But I think when you consider the Kerr space-time or wormholes or some other space-times, the ranges were quite distinct. And this could essentially be a good enough parameter to ascertain what sort of black hole it is, or what sort of space-time it is.
Oh, interesting. Okay, thank you.
Yeah, of course.
Right. Any more questions? Okay, if not, then let's thank Haider and thank you, Haider, for taking the time out, and thank you. I know that you will be approachable for our students if they have any follow-up questions, and hope to see you next time here in Lahore. I mean, this time also we were planning that you would actually come here in person, but somehow you couldn't make it.
Yeah, unfortunately I could not, but yeah, hopefully sometime in the future when I have more research from my PhD to share, I would certainly like to share with people at LUMS.
Wonderful. Thank you, Heather. Have a good day,
Yeah,
and
you
have a
too.
great day, everybody. Bye-bye.